So this is going to be an introduction to Python. There'll actually be sort of three separate parts to this. First, we'll talk about Jupyter, Jupyter Notebook. And the reason for that is we'll do that before Python because a lot of the lectures are going to be in Jupyter. And so we figured it'd be good for you to see how that works before we start actually doing anything else in it. Then I'll spend more time talking about Python itself, the language, and then hopefully if there's time, well, there will be time, I'll talk about Python and data science. So Ariel already talked a little bit this morning about why you might want to use, and why we are using Python as the primary language of instruction. And so I'll talk a little bit about Python in a data science context. So hopefully you're all seeing what I have here, which is the same Jupyter lab you see when you first log into the hub. And so if you haven't already done this, if you click on curriculum over here on the left side, find Monday Python. If you click into that, and then if you just double click the Jupyter Notebook notebook, that's what we'll be looking at here for the next maybe 20 minutes. I'm going to be moving fairly quickly. One thing I've tried to do is be very verbose in the notebooks, at least the first two. The third is only slides. And so, you know, there's people from lots of different backgrounds here, and so I will try to move at a reasonable clip. But if you do miss something, or if I'm not clear, hopefully the text, which will be in much more detail than what I say, will get you up to speed. And if not, then feel free to message me in Slack afterwards, or ask a question in the channel, and someone else might be able to help you out as well. There's probably many people here who've used Jupyter Notebooks before. So let's talk about the Jupyter Notebook. Oh, and sorry, one last thing I will mention. If for some reason you didn't realize there were two talks going on at the same time, they're sort of parallel basic and advanced tracks. So if you're already familiar with the Jupyter Notebook, have worked in Python before, you might find the high performance Python talk that Ariel's giving more useful. They'll both be videos later, so there's no harm done. Of course, you're welcome to watch both. But just to let you know, in case you're in the wrong place, this will be a fairly introductory overview. Okay, so let's talk about the Jupyter Notebook. What is the Jupyter Notebook? It's this thing you're looking at right here. A good definition comes to us straight from Project Jupyter's website. It's an open source web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. Uses include data cleaning and transformation, numerical simulation, statistical modeling, data visualization, machine learning, and so on. As an aside, if you haven't noticed this already, the creator of Jupyter Notebook, previously IPython Notebook, Fernando Perez, will be giving a talk later today, I think right after this, which I would definitely recommend. It won't be a technical talk. It'll focus more on sort of the motivation for the project, the benefits to the community, et cetera, but it's very much worth going to. I think it's a fantastic talk. I'll focus more on the mechanics, just very basically. So what is a Jupyter Notebook? It's an interactive notebook that lets you, as I just said, put all kinds of stuff together in one place: code, equations, visualization, narrative text. It's particularly helpful in science because in a sense it lets you write a scientific paper in a better way, where you can actually embed all of your code, figures, text in one place, but also very useful for prototyping and for instruction, which is why we're using them so heavily. I mentioned IPython Notebook, which was the sort of the predecessor of Jupyter. You may also be familiar with R Markdown or R Notebooks, which are sort of similar concepts. They're not exactly the same, but the idea is you have this sort of interactive way of laying out your code and text. Now, some people think of Jupyter as a Python project, and it did start out as a Python project, but the current instantiation of Jupyter does actually have support for a whole bunch of languages, I think like 30 or 40 possibly. You have to do a little work to set up the language kernel you want, but once you install that, anytime, so if you notice the launcher here, right? So you probably will only see Python 3 as your options, but if you install other kernels, then you could create an R notebook, a Julia notebook, et cetera. And I won't talk about it here, but there are even ways of having a notebook with multiple languages, so you can actually pass data from Python to R and back, for example. I kind of left off there, I guess. Okay, so that's the notebook big picture. Now, what is a notebook composed of? It's made up of cells. What are cells? Cell is a chunk of something, text, code, etc. And you can see here in the notebook, we have this cell highlighted, and the blue over here is the border that's highlighted. So this is all one cell. Everything that has blue here on the left is a single cell. If I click down here, that's a different cell. That's another cell, that's a cell. And so each of these are created and edited independently. We get to choose what we put in them and when we execute them. There's two types of cells. There's actually others, but the two important ones are markdown cells and code cells. So markdown, you may be familiar with, is a lightweight markup language that allows us to style plain text. So you can have headings, lists, etc. It's not like full-blown styling. It's not like HTML, but you can sort of give your text basic style, which is very helpful. And the cell you're reading right now, this right here, is a markdown cell. So if you are viewing this on the web as a static document, you won't notice, it'll just look seamless, right? There won't be any sort of anything to suggest that this is where one cell ends and another begins. But since we are editing this, and you hopefully all have found this, and you can double click on this cell, and that will change the view. And all of a sudden this happens, and now you can actually see the markdown that a moment ago was rendered. So here's the actual code, right? And I can change this. I could edit this, and once I'm satisfied with my edits, I can render it. So I can either go up here and press this run button, or I can go to run from the menu, run selected cells, or I can hit Control Return, which is a keyboard shortcut, which does the same thing. So lots of different ways to run cells. Okay, so that's sort of basic getting into a cell and executing it. That's markdown cells. That's plain text. And when you run a markdown cell, it'll just render it. So you can see now that a moment ago what was just plain text, right? This is how you represent a heading in Markdown. So when I execute that now, those headings are actually rendered nicely. So you can build you can build a fairly nice looking document really quickly this way. What about code cells? Well, no surprise, code cells contain code. As I mentioned, the language in those cells depends on what kernel you're running. For most of this course, it will probably be Python, almost always. And so here's what a Python code cell looks like. And so you can see that there's nothing, and I'm not going to talk at all about code because we'll talk about Python certainly shortly. But here's a cell with some Python, and if I execute that, then you can see this hello world message prints. So I executed, and the way to think about this is executing a code cell is exactly the same as what would happen if you were, let's say, in an interactive prompt in a shell in Unix, or like if you're used to R, if you're like in RStudio or just base R, and you have that command line. And so every time you run a cell, you can basically think of that as like you're taking all the code in that cell and pasting it into that command line and running it all in one shot. So it's essentially executing all the code in that cell, which also implies that order matters, right? If you execute a cell higher up on the page before one further down, then you can think of it as if you type that into your prompt first, but you could reverse that. So if I were to go down here, for example, and run this cell, it might not work because it might be expecting something higher up on the page, right? So you kind of have to think about it. The fact that it's a linear document does not mean that it has to be executed that way. And that's important to keep in mind. Like it's the order you execute the cells in is the order they run in. Although it's generally good practice to make sure before you share a notebook that when you do run it start to finish, you won't get any errors. Okay, so code versus Markdown, that's an important distinction. Also, code cells are nice because they will, if they generate images, for example, or tables, then Jupyter has the option to render those images in line in the document. So provided that the language you're using supports that, that should work. So here's some Python code, for example. And I'm just generating, again, I'm not going to talk about what the code does, but I'm just generating a histogram. And the key point here is Jupyter has these, what are called magics. And this one just says, hey, when matplotlib, which is Python's main plotting library, produces a figure, plot that in line. So put that in the document instead of popping up a different window or just handing it off to the operating system and saying, this is your problem now. So when we run this, I guess it's already executed, but when I run that, you get this figure momentarily, and it's inside the document. It's just below the cell, which is nice. You can have the figures laid out alongside the code that generates them. So executing code cells, just like with Markdown. So if you're in the code cell, you can click this run button, or you can go to run selected cell, or you can just hit control return once you get comfortable with keyboard shortcuts. Okay, so those are the two main kinds of cells. There are different modes, different ways of interacting with the notebook. Two modes, edit mode and command mode. So notice right now, I can't, if I start typing, it doesn't, well, you have to trust me that I'm typing. It doesn't do anything. In fact, okay, actually, I just created this cell. Nothing, I can't edit the content, and that's because I'm in command mode. If I click on a cell to enter it, and so it looks like this, I'm in edit mode, and I can edit the contents of the one cell. And there's one set of keyboard shortcuts and commands that work in this mode. And if I'm not in this mode, so if I'm in command mode, there's a different set of commands I can use. And command mode you can think of as managing multiple cells. So if I want to move, for example, cells, that's a little different from, so well, I'll get to this, but JupyterLab is a little different from base notebook, which actually has some more options on the menu. But you can, from the menu, go to edit, and then you can, I think there's a keyboard shortcut, I'm not remembering for this too, and move cell up, for example, right, or move down. You can create a new cell, so if I hit V, V will create a new cell directly below. Or sorry, V is space, right, B will create a new cell below, right? X will remove a cell. And so the point is, if you're in command mode, you're performing operations on entire cells. In edit mode, you're editing the content of individual cell. And you'll notice the color changes. So when I'm in edit mode, you see the border is blue. Or sorry, when I'm in command mode, the border is blue. And if I, oh wait, okay, I'm sorry. This is another change I'm used to the base Jupyter notebook. I guess JupyterLab is a little bit different. So ignore that. The colors apparently are similar. That doesn't really tell you what mode you're in. What you can do if you want, like there's some things I say here that aren't quite right for JupyterLab, but you can, well, so, oh, here we go. Yeah, open with notebook. I think that will open up maybe the traditional notebook. Anyway, it doesn't really matter. There's very little difference between these two. Just some of the things I write may not be quite correct. And there are also lots of shortcuts. So you can see I'm using the mouse to navigate and move around, but there are lots of keyboard shortcuts. Unfortunately, this also doesn't apply here. There isn't actually a keyboard shortcut reference here. I'll have to dig around for that. Sorry, I should have verified this earlier. But you can Google them, and there are lots of keyboard shortcuts that, over time, it's helpful to learn because then you can interact with this very quickly. You can delete cells, move them around, et cetera, very quickly just by using the keyboard. So there's a question about what the difference between JupyterLab and Jupyter Notebook is, and I'll talk about the difference in a bit. And another question, this is important for notebooks that are shared like this one. Do the edits you make get saved to the version everyone else has access to? No. Any changes you make only apply to your document. One thing to be aware of, though, so you can't screw anything up for anyone else. However, be aware that you can screw things up for yourself, and there's no like point and click way to retrieve the original version. So if you're going to make edits, not a bad thing to do is to right click on the thing you're going to edit and press duplicate, and then you'll have a backup copy in case you mess something up and you don't remember what it looked like. You can also clone directly from GitHub, but we haven't covered GitHub yet. So assuming that that's not an option right now, you might just want to duplicate the notebooks before you start editing. Okay, let me. Just answer this. Okay, so one thing that's really nice about Jupyter is it's highly extensible. So it's not, as you're seeing it right now, and in general, I wouldn't quite, sometimes people think this is like an environment you should start writing a lot of Python code in, and I would not recommend that. Right? So it's not really much of an IDE or integrated development environment. It's not a tool that I would recommend people write like serious code in. it does have basic editing functionality, like you can see syntax highlighting, right? So you can see that like it highlights statements like from and import. In Python and other languages, you get similar syntax highlighting. But there's lots of nice things that good editors provide to you that, at least out of the box, you don't get in Jupyter. So I would not recommend this as like a way of working in general. It has really nice uses in the context of instruction, prototyping, just experimenting with stuff, and that's how I personally use it. I think many people use it that way. But do be aware, like I would not suggest that like you just start writing all your Python code in this environment. But you can customize it heavily, so you could potentially add all kinds of key bindings and make it behave in much more sophisticated ways. I'm not going to talk about many of the extensions that are available here, but you can browse the links. If you click on these URLs, you'll get a bunch of lists of different extensions. You won't be able to install them in the hub, but if you run Jupyter locally, then you will be able to. So on your own computer, you can install any extension you see. We did install one extension though, because I kind of want to show you this. This is kind of neat. There's something called IPyWidgets, which lets you hook up. Let's say you have a plotting function like this, and it has these parameters, mu and standard deviation in this case. You can connect little widgets in the notebook to the parameters of that function, and that makes them interactive. And so if you look up here, right, this is the code to plot this static histogram. And this is very, very similar. We've just embedded it in a little function. And this one line here attaches this function to these little widgets. And so when I execute that, and hopefully this works for you, now I get something that I can actually interact with. And that's incredibly powerful because if you're like prototyping, let's say you're running a simulation and you want to know what happens if I change this parameter, right? You can actually do that in real time and observe the differences. Like, so if you want to see the difference in these distributions as I increase the standard deviation, for example, you can do that. So it's an incredibly useful tool. Lots of other features in the notebook. I'll just mention a couple. Again, we don't want to spend too long on this. LaTeX is supported built in. So if you're in a markdown cell, right, here's the LaTeX equation. You just enclose it with either a single or two dollar signs. When you execute that, LaTeX will be rendered nicely for you. So that's super nice because if you're doing some math, then you can just write LaTeX equations directly into the notebook. There are these things called magic commands, which can make our life easier. I showed you one above to plot matplotlib inline. There are other useful ones. For example, time, which helps you time whatever you're doing. So if like you have, actually, let me show you this. So if like I create a new cell and so this takes no time at all, of course, but the point being, like you can profile that cell very easily, and there's a bunch of these little helpers that will do various helpful things, and you can click on this link, and it'll take you to discussion in the official documents about magic commands that show you all of them. You can export Jupyter Notebook. So actually, again, I don't know if this is true here. Okay, yeah, export notebook as, and you have all these options. So you can easily export the rendered document to PDF, to HTML, etc., which is nice. You can also execute system commands. So on any operating system, I believe, if you prefix a command with the exclamation point here, then that will run as if it's in Windows, it'll be a command prompt. On any Unix or Mac system, it will be like you're running the line in shell. So here, if I type, so this is just ls just shows me what files are available, and if I just list all the IPyNotebook files available, that's what you get. So this is running as a system command, and then the output is printed back here. Now you want to be careful with this because it is exactly like you're running a shell, right? So you can RM, RF, everything for those of you familiar with Unix, right? It's not. There's no sandbox here. Like you can destroy your system just as easily as if you had a command prompt open. Here you can't because you are sandboxed here in the sense that you won't be able to harm anyone else. You can only delete your own files in your hub. But if this is your system, then do be aware that what happens in a Jupyter Notebook when you run a system command happens in real life, right? It's not a sandbox. There are custom themes, so you can change the look quite dramatically. It's kind of neat. You can give a totally different appearance to your notebooks, and also you can customize for certain aspects. You can change like for example, only the font size within cell mode, right? So like when you're in this one, maybe you want that to be bigger, but you don't want it font to change when you're rendered. So you can do things like that. Okay, so that's just basic overview of Jupyter Notebook. I would suggest you just recommend, or you just experiment if you haven't worked in a notebook before. Again, you can't really break anything for anyone else, in the hub at least. So don't be afraid. You might, like I said, want to make a copy of the original notebooks before you start messing around. But otherwise, you can't really do anything bad, I don't think. Now, there's a question about Jupyter Lab. What's the difference? So Jupyter Notebook is a fully functional environment for writing and editing notebooks, like you're seeing here. But its emphasis is really focused on like a single notebook. There's not much, or there wasn't much support historically for other things that you might want to do surrounding the notebook. For example, you can see on the left here, we have this pane that has multiple notebooks. I can actually rename them, copy them. And that functionality is either non-existent or very clunky in the notebook. And so a couple of years ago, the Jupyter team started this project Jupyter Lab, which is in some ways, if you're familiar with R, you can sort of think of it as like an effort to sort of give the notebook kind of what RStudio provides for R, which is a slightly better, more user-friendly environment for managing files, data. I think there's also, I believe there's a variable view, so you can actually look at the contents of variables. I hope I'm not making that up. And so there's not much difference as far as the actual notebook goes, because in essence, this is just wrapped around the notebook, the standard notebook interface. But the plan is, I think, that they do intend to replace, eventually the notebook will go away. Right? Jupyter Lab will be the only supported version. And there's no real downside to it. As you saw, the interfaces may be a little bit different, but these aren't, this is just getting used to. So I would recommend locally, you may as well run Jupyter Lab. There's really no downside. You get like some extra functionality. But just do be aware of that distinction. The only difference is when you fire this up from your command line, assuming, and I won't cover that here just because of time, but if you can install Jupyter and then you type Jupyter space notebook instead of, or Jupyter Lab, right? And that would fire up one or the other as a server on your computer. Let's see a couple of questions. Do you have a Python IDE that you were kind of learning in? I personally use VS Code, which is a Microsoft product. It's free. A lot of people really like VS Code. Sublime, Atom, or other ones that people use, PyCharm. But yeah, I think VS Code is probably the single most popular IDE. Not just for Python, but it does have excellent Python support. Is the widget feature only for Python, or is it something that's compatible with R as well? Well, so this particular implementation is specific to the language. There may very well be, it would not surprise me at all if someone has built a equivalent plugin for the R kernel. I don't know offhand, but so it's certainly something that could be done. Whether it has been is I think, an open question. Once you open edit mode, how do you go back to command mode? There are several things you can do. Easiest is probably just to click outside that cell boundary. So if you click over here on the side, oh, interesting. This is also a Jupyter Lab change. You can hit escape. Escape is probably actually the easiest. So click escape, and that will notice that in this case, if you're in a markdown cell and you hit escape, it doesn't automatically render it. So you're outside the cell, but it won't automatically render it. So you'd have to hit run if you actually wanted to render that. And the same thing with a code cell. It won't execute when you leave the cell. You have to do that yourself. Okay, so let me close those. All right. Okay, so that's just a very basic overview of Jupyter. As I mentioned already, I don't want to give you the impression, some people are kind of prickly about this, and with good reason. I think I don't want to give you the impression like Jupyter is like an editor you should like do all your writing coded, right? So I don't use Jupyter. I use it when I'm prototyping, like if I'm trying out analyses, it's nice there. I use it for instruction, a couple of other uses, but when I'm writing like actual Python code or package that I tend to distribute or just run locally, then I will usually use VS Code or something like that. Having said that, of course, like whatever works for you. Like if you find this meets your needs, then great. Just be aware that there are much better fully featured environments for writing code. So this is not the right tool for everything. Okay, and last thing is there's all kinds of options for help and Google. Oh, sorry. So if you launch Classic Notebook, this is, if you do this, then I don't know if you can actually still see this probably. Then everything I wrote in the notebook will apply. The parts that don't make sense, like if you hit H, you'll get a keyboard shortcut reference. But there isn't really much reason I wouldn't recommend necessarily using the notebook. That doesn't seem like a good enough justification. Okay, so are there any quick questions about the Jupyter before we switch gears and talk about Python? It was actually a little longer than I wanted to spend, but that's okay. All right, so let's talk about Python. So if you double click on that intro Python notebook, then this should pop up. And as I mentioned, I will be moving fairly quickly, so don't be alarmed if something doesn't make sense. There's lots of text there you can peruse, and if it doesn't make sense after that, then feel free to ask questions in the channel. I'm assuming, by the way, some minimal programming experience, right? So I'm not going to like explain, for example, what is a variable. I will assume you have a little bit of experience in some language, Python or something else. So this is really sort of an overview of how you do things in Python that you may already be familiar with in other languages, and some strengths and weaknesses. Having said that, the fact that it's a tutorial and it's introductory does not mean it's easy. I do want to emphasize it. Like, I wrote this deliberately to span sort of a wide range of expertises. So there might be parts of this, if you're fairly new to programming, some of the later parts might be, really incomprehensible. Don't worry about that. Like, there's no expectation that, like, spend like 10, 20 hours programming and understand first time you see like object-oriented programming what is going on. That is not the intent. This is meant to span, this is meant to, hopefully there's something in here for almost everyone, but don't be surprised if some parts are either too basic or you have to spend a couple hundred hours programming before they really start to make sense. That should not shock you. We talked about imposter syndrome, right? Like, you should not have the illusion that like anybody just like picks up a programming text, reads it, and is like, okay, now I'm not a programmer, right? It takes everybody a long, long time. So do not feel bad if it's frustrating and difficult. That's not unusual at all. Okay, so with that caveat, let's talk about Python. Python is a programming language, and it's a nice programming language in many ways. It's easy to learn, it's high level, it's general purpose, and it's dynamic. So that's a mouthful, and we can unpack that. So let's take each of these in turn. So when I say easy to learn, as I just said, programming is hard, right? So nothing is really easy to learn in an absolute sense. But relative to other languages, at least, Python is kind of high level, which I'll mention in a sec. It's readable, and it forces you to use white space or spaces in a way that makes the language easier to read. So here's a Python function. I'll talk about functions in a bit. I'm not going to explain this code at all, except to point out, right, that even if you knew no programming at all, you've never seen anything like this, parts of this are actually still not completely incomprehensible. Like, you could see 4-word in word lists, right? These are English words, and you might actually, just from that, understand what's going on, right? Maybe like for every word in that word list, you're doing something. And you'll notice that there's this indentation, which Python actually forces on you. It's not like I employ good practices, so I indent my text. You have to do this, whether you like it or not. And it forces everyone's code to look more similar and to make sure that it's easy to understand at a glance the structure of the code. So there's some nice features of the language that makes it lend itself to be fairly easy to learn. And this is sort of like a kind of silly Pig Latin example, just to show you now that this is, we can, if I run this, it loads into memory this function, and then I can actually, in this next cell here, execute that. And you can change this if you want, and rerun, and that should produce. Okay, so this probably chokes on that question mark. Yeah. So it's not a perfect Pig Latin function. Feel free to improve it if you want, if there is such a thing as perfect Pig Latin. But hopefully you can see that it's sort of, it's fairly easy to read as programming languages go. Okay. I said Python is high level. What does that mean? Well, if you have any experience with languages like C or C++, or even Java to some degree, you're probably used to doing things like declaring the type of the variable you're using. You might have to allocate memory, right? So you might have to say, please reserve 20 bytes for this variable, and you have to free it up when you're done. You will do none of that in Python. It's all done magically for you. So that's great, though there is a cost to that, and the cost is Python is going to be a little slower than let's say, C or something. Now, it won't be noticeable generally, but if you decide one day you're going to write a video game engine, Python is probably not the language you want to do that in. But probably most of you are not writing video game engines, so we don't have to worry about that. Python code is dynamic. What does that mean? Well, so many languages are compiled just to say that before you can run the code, you have to actually compile it. And there's a compiler that's a program that takes your code, analyzes it, and converts it to some machine bytecode that you can actually execute. And one of the things, and that's annoying because it takes time. But one of the things you get when you do that is that the compiler can do some optimization. You can basically make sure that you're not making certain kinds of errors. Python and many other dynamic languages don't do that. There's no compiler. When you start running Python code, it is interpreted line by line from the top. It will just start running. And so that's really nice because it's fast. You don't have to wait for compilation. It's very easy to iterate. The downside is, well, it's not really a downside, it's a choice. But with that, what you get is that there are certain mistakes that the interpreter will not catch. And for variables, which I'll talk about in particular, can change type on the fly. So you might think you have a string, but it's actually an integer, and then that breaks your program. The upside of that is you don't have to say, hey, this is a string, or this is an integer. So as you'll see, writing Python code is much easier in some ways. It's faster than other languages, but there are costs. And lastly, it's general purpose, meaning lots of languages are designed for very specific niches. Many of you probably work in R. R is a great language for data analysis. It's not a great language, I would say, for much else. It's very narrowly developed for that use case. Python, by contrast, you can do almost anything in Python. Now, obviously, like I said, some things it's really not the best choice for. You shouldn't write game engines in Python. But for a really wide array of applications, it's a very good language. Not maybe the best, but it's good enough that you can do almost everything you want. And it's really nice to be able to work in a language where you don't have to change, you don't have to like learn a new language or switch to a completely different environment with different concepts every time you want to do something slightly different. So those are some benefits of Python. Okay, now let's talk about what the actual language looks like mechanically. And again, I will move fairly quickly. Feel free to ask questions. I can't promise that I can answer them, but I am paying attention as I go. Okay. So variables. How do you assign the variables in Python? And so now I will be executing these code cells as I go, and I encourage you to do the same. If you get an error message at some point, most likely you didn't execute something above that the code depends on. So kind of want to follow along and hopefully make sure that you're executing. And feel free to experiment too, right? I mean, like the whole point of this is you can change anything in this, rerun it and see what happens. Okay, so super easy variable assignment in Python. Here's the name of the variable, equal sign, and the value. That's it. Notice no type declaration. I'm not saying, oh, 3 is an int, it's not like int's my favorite number equals if you're used to statically typed languages. This is like pretty much the least amount of typing you could do to declare a variable. And so once you run this, you now have a variable in memory called my favorite number, and its value is 3. And this idea, which I just mentioned, that you don't need to declare the type is sort of inferred. The interpreter figures out what the type is when it needs to, is called duck typing. If it looks like a duck, talks like, or quacks like a duck, it's a duck, right? And so the Python philosophy is, we don't need to know ahead of time what the type is. We'll just try running the code we want, and if it fails, then we've learned that it's not a duck. Some people hate this, some people love this. It's a different philosophy. It's not good or bad. Like there are cases in which this is really, really helpful. One of which is when you're doing data analysis and you're not releasing something that needs to be really fast and really, really well constructed into production. But there are different philosophies, be aware. We can always print variables. So Python has a built-in print function. So if you just wrap the variable with print and run that, you'll get. Now you might look and say, well, why did I need to do that? I did this, why can't I just execute the cell? And you can. So here, for example, notice the last line here is my favorite number. And if I run that, essentially that's equivalent to calling print. But this is a notebook thing. This is not a general Python thing, right? Like it's not like variables will magically print themselves to the screen. It's just that when you execute a code cell in a notebook, the very last line, the output of the very last line will be displayed. And so you can skip that print step. But notice here I have another string, and that one is not printed because it's not the last line. So it's only the output from the last line you execute that's returned. So be aware. Okay, now there are built-in types. You're probably used to things like strings, booleans, integers, and so on coming from other languages. Python is exactly the same. Out of the box, you have a number of built-in types. So integers, for example, you already saw one, right? So if I want an integer, a whole number, I just assign that to the variable, done. Now I have a variable age in years with the value 30. Arithmetic works as you probably expect coming from any other language. So here, divide age in years by 2. I run that, I get 15. Actually, sorry, let me just, actually just want to clear the outputs. There we go. just so you can't see what's coming next. I think for when you load it up, you shouldn't have the apps displayed, although of course you're welcome to run them all in advance. Floats, so floats, which you can think naively as a decimal number, that's good enough for now. There I assign a variable, it's almost pi, and I can, arithmetic works just the same as it does on integers. And so here I can also round, so Python has a built-in round function. If I round that almost pi variable, now I get back an integer, the value 3. So floats, integers behave more or less as you would expect. Strings are nice because Python provides a lot more functionality in the string type than some other languages do. So here we'll just create a string called country. I'll give it the value Madagascar, and we can ask, there's a built-in function len, which you can apply to all kinds of objects, including strings. Not everything, but many types. So if I ask what is the length of this variable country, it's giving me the length of the string. Strings also have all kinds of what are called methods implemented on them. Notice the difference in syntax. I'll come back to this, right? So above we're calling like len of country. This is a functional syntax. But here you have this dot notation. So we're taking that string and we're calling it like string dot upper, and this is gonna return an uppercase version of that string. And there are many different methods, like you can count the number of occurrences of the substring A. Again, feel free to experiment with this as I'm going through it. So if I like change that, I get 0 because that substring does not occur in Madagascar. You can replace substrings. So here I'm going to replace any occurrences of car with the string truck. And again, Madagascar truck, wonderful. Lots of methods like that implemented on strings. There's lots of things you can do with strings out of the box. Booleans. Every language has Booleans. They do exactly what they do in other languages. They just represent the truth status of something. So there are only 2 values a Boolean can take on, true or false. Notice the capital, right? So in Python, those values are true like this or false, and those are the only valid values. Not true, that doesn't work. You can't use lowercase t. You can do 1 or 0, but that will make it an integer and not a Boolean. So false and true are the only valid values for Boolean. As you may know, probably know if you have programming experience in other languages, you can perform logical operations on all kinds of things, and they will evaluate to a Boolean. So for example, here I'm saying, get the length of the string apple, and then I'm asking, is that value larger than 2? And you might already gather, yes, it should be true, right? Because like there's more than 2 characters in apple. Okay, here I'm asking, is the product of 719 and 1.0002 2000? The answer is no. And so Boolean operations are super useful, and we'll talk about them a little below it when we talk about control flow, conditionals, and things like that. Now, this is a little different from some languages, although many languages have something like this. None is a special type in Python. It's equivalent to null. If you come from languages that have a null value, it basically says there is no value. Right? So you want a placeholder in some sense for a variable. You want to initialize a variable, but you want to say it has no value. So here I'm creating a variable name, but I'm giving it the value none. None is not the same as false. That's a common misconception. I just noticed there's a question, how are spaces used? I'll get to that in a second. None is not false, and you can see that if I ask, is none equivalent to false, the answer is false. And they have different use cases. None is no value. It's not that it's false, it's that there's no value assigned. False is a value, it's just a negative in the case that something is not true. Okay, so those are the most basic data types you have out of the box in Python. Why does 719 require 2? Oh, so yeah, so sorry, I should clarify. This is an assignment, right? So this is saying assign the value none to the variable name. Equals is an equivalence operator. So this is asking, are these 2 things the same or not? So so it evaluates true or false. So these are different. And that's going to be true in most languages. I think like it doesn't always look like it might have a different operator, but every language is going to have this concept of equivalency that you can test against different variables. So those are the basic data types. But that's not enough to really do much work. You can't really live very pleasant life as a developer with just strings and integers. You often need containers and collections that can hold other objects like strings and integers. And so Python provides built-in support for quite a few of these. There's lists, which are the most common. A list is an ordered heterogeneous collection. What does that mean? So order means that the list has a memory of the position of its elements are inserted in. So if I create a list and I add one element and another and another, the order will be the same. And I can refer, as you'll see, I can refer to those elements by their order, their index. And it won't change magically. It's not like if I go away for half an hour, come back, that list is like scrambled itself, right? It will not change unless I explicitly move things around in the list. And heterogeneous means that the list can contain elements of different types. So a list does not have to be all strings or all integers. It can have one integer and 10 strings and any other, any combination of any kind, number of different types. So to initialize a list, we enclose the values we want in square brackets. Or you can initialize an empty list by without any values. So that's an empty list. But if I initialize it like this, what I'm saying here is create a new list called random stuff and store inside it the values 11, apple, 7.14, and banana. Okay, so I run that, nothing happens, but that's because I'm not printing anything, right? I'm assigning to that variable this list. Now, how do I get information out of that variable? So let's say I want the ith element in the list. So I want the second element. We use the same kind of syntax. We enclose the index, the position we want in square brackets. So here I'm basically saying, give me the second element. Notice I say second and not, you might think it's the first, right? Because it's one. Python, like most programming languages, but unlike R and MATLAB, indexes from 0. So the first element is 0, not 1. This can cause confusion if you're coming from like R and MATLAB. There's no better or worse here. It is what it is, right? There's no reason like why 0, 1 would be well. People have holy wars over this issue, but we don't care. Like it is 0, you have no choice about the matter. So this is saying just return the second element in the list, the element at position 1. And there you see it, apple, right? Just like it was here, this was indeed the second element, so we know that that works well. We can also slice lists, so we don't just have to pull out one element at a time. We can use what's called this slice syntax, where this colon basically takes two values, one on either side, and you can read this as from here up to here. So when I say this, I'm saying, give me the elements starting from position 1, so the second element, and ending just before, so this is exclusive, it doesn't include the element position 3, or the 4, it stops right before it. So if I run that, I will actually get 2 elements. You might think 1, 2, and 3, or sorry, 2, the 1th, the 2th, and 3rd element, but it's actually, it includes the first index, but excludes the second. It's up to, but not including. Again, this is not a question of like, whether you like it or not is irrelevant. Like that's how it is, and so you just have to be aware of that. Okay, so we've seen how to create variables or lists and how to access information. How do we assign values to list elements? How do we overwrite that? And it's exactly the same syntax, just with an assignment. So here we say random stuff, assign the value 14 to the first element of random stuff. And so what we're going to print is the line before the assignment, or we print the first element before reassignment. And was that, yes, indeed, it was 11, good. And after we assign 14, we print the same thing again. Now it's 14, right? So you can see that that value has changed. We can also append to a list. So lists in Python can grow and shrink dynamically. We can append to a list with the append method. So here's our list, and we append to it this value 88. And now notice we have this new element in the list. Okay, so those are lists, super useful. You will encounter them all the time. Right? They're extremely powerful. The other super common, super important data structure in Python is a dictionary. Many languages have, probably most major languages have an equivalent. They're, I think, almost never called dictionaries, but you may have heard of associative arrays or hash tables. Those are sort of, they have some subtle differences maybe, but basically the same idea. And a dictionary or an associative array or hash table is a mapping. It's a mapping from keys to values. So what you're seeing here is a dictionary called fruit prices, and this is how we initialize it with the curly brackets, the braces. And notice that you have these pairs, right? So you can think of it as like a collection of pairs where it's a mapping from, in this case, apple to a value. So this is saying that at the key apple, we're storing the value 0.65. At the key mango, we're storing the value 1.5, and so on. And notice that dictionaries are also heterogeneous, both in the keys and the values. Now, there are some restrictions I won't talk about here on like what can go into keys. Values can be anything at all. But notice that integers are valid keys. So I can have keys that are strings and integers in the same dictionary, and the same goes for the values. So let's run that. Okay, so now we have a dictionary sitting there. How do we index dictionaries? How do we get information out of them? Very similar to lists, in fact, identical, same syntax, the square brackets, but now we're passing the key. So if I want to know the stored value associated with the key mango, then I put that key mango inside the square brackets, run that, there comes my value that was stored. Dictionaries, though, cannot be indexed by position, so they do not maintain lists. They're unordered. There is an ordered dict structure in Python you can use if you want, but the sort of base default dictionary built in does not give you that. So if you'll notice here, if I do this, right, you might naively think, okay, that'll give me the first pair above. It should be also, it should be the equivalent of apple. But no, this does not work because there's no key 0. Notice that you could use integers. So it's not that the dictionary is not allowed to have integers as keys. That works. Why? Because I explicitly created a key at 5. Now, I will say it's probably not good practice to use integers as keys in dictionaries because it's confusing, right? Because this could be a list. And so it just minimizes confusion if you try to avoid using integers as the keys in your dictionaries. But sometimes you need to, and that's fine. How do you update a dictionary? Exactly the same as you would a list. You pass the key, basically are pointing to the chunk of information you want to change the value of. So here, I'm actually creating a new, there was previously no orange key in the dictionary, but I'm saying, okay, at the key orange, set the value to 0.5. And if there was a value there, sorry, if there was a key already defined, then it would overwrite the existing value. And if there's no key, then it'll just create a new value. So we see both of those here. We're going to create a new key for orange, and we'll overwrite the existing one for mango. So now that's the state of our new dictionary. Okay. Last collection I'll mention, there are many others, but these are sort of by far the most important ones. A distant third is the tuple. A tuple, many people, actually, you can go a long time in Python without ever really needing to know what the difference between tuples and lists are. I'll just mention it because you might see this, but don't worry too much about it. A tuple is, in almost every way, a list. It's initialized with parentheses and not brackets. The big difference, and there are reasons why this is useful, but I'm not going to cover it here. The big difference is the tuples are immutable, which is to say they cannot be modified once they're created. So this, just to illustrate that, right? So I initialize this my tuple variable. Now, if this was a list, I would be able to do something like this. I would say, okay, I want to change the value at this element to that. But that will not work because you cannot assign new values to tuples. Tuples are basically, once they're created, that's it. And again, there are reasons why that's quite helpful. The main one being you can save memory if you know that you're only ever going to need this one thing that doesn't change. But you can go a long time without ever really needing to be very clear on that distinction. So just be aware there are these things called tuples. All right. So let me, actually, maybe this is a good, yeah, you know what, it gets a little more difficult after this. So why don't we stop? Why don't we stop here, take a 10-minute break, let's say, and then we'll start up again at like just before 3 my time, but 1 p.m. I guess Pacific. So let's stop here and come back in a bit. And feel free to ask questions. And I will probably stick around during the break. So now is a good time if you have questions. I won't say anything that like anything after this depends on, so don't worry about like leaving the room. You might miss something. Actually, maybe I'll just type well, let's do that. If you have questions, I'll just type answers. some of these questions actually I think are good, and I want to actually answer in a couple of minutes when everyone's back. So if I'm not answering your questions, probably because I actually want to come back to it. Okay, all right, let's start up again. Yeah, lots of questions. Hopefully, I think I got to most of them. One question was, which I thought was worth bringing up here, is there a magical way to get Jupyter Notebook to list expected attributes at a package level? So that can actually mean a couple of different things, but let me show you one of them and then I'll get to the other in a little bit because we have content. So if you have like a function, for instance, like len, if you're inside the signature and inside the parentheses here and you hit Shift Tab, then you'll get help popping up. You can also bring up help for that function by executing the cell, the question mark before it. There's also a question like, can you look at like what all the attributes are in the package or at an object? And the answer is yes, but let's hold off because I'll get to that in a second. Other questions I'll get to at the end. Sorry, I tried to get to as many as I could. Okay, so let's pick up where we were. So, and I might start to, well, I won't speed up, but I mean, the content gets a little denser. So again, I do want to reiterate, like if you don't follow what I'm saying from here on out, or even if some of what I already said doesn't make sense, that's totally fine. Right? I mean, this is not easy stuff. Like you can't just sit down and expect to understand like object-oriented programming unless you've had some programming before. So, okay, so I mentioned, we talked about like basic data types and collections. And now I have a little bit of a confession, right? So in many languages, there is actually a distinction between like primitive or basic data types. Like Java has 8 data types, and that's all you get. You know, you're out of luck if you want something else. You can create classes, which are a kind of data type, but they're not primitive. They won't behave the same way as the ones built into the language. Python is different. So in Python, actually, everything is an object. Strings are objects, dictionaries are objects, lists are objects. Everything is, in some sense, the same kind of thing at the end of the day. It's just that different objects have different behaviors defined on them. We'll talk about like how you define those things. But the critical point to note is just that there is nothing special about strings, right? And that has implications we'll explore. One thing to kind of be aware of in Python, because it's a deeply object-oriented programming language, everything is an object. Most of your interactions with functionality in Python are through objects in one way or another. And so you may have noticed that there's kind of two syntaxes you've already seen, right? So you've seen this one here, like len of this list. That's a sort of functional syntax. You'll be familiar with this coming from R MATLAB, for instance. So we're passing in a list as the argument to the length function, and the result comes back. But that's different from what we saw when we used this method lower on strings, right? So here we define a string called phrase, and then if we call the lower method on a phrase, we get back this result. So why this difference? Like why the functional syntax and this dot syntax, dot notation? What's the difference? If you're coming from another object-oriented language, this will make perfect sense to you. You'll have seen it before. If you haven't, the way to understand this is that dot basically says, you can think of it semantically as like look inside of this thing, right? So you can think of like lower as actually being that function that's bound, it's contained inside the object. And so what we're doing is we're saying, hey, take this variable phrase, and then inside it, look for a method, which you can think of as a function. So this, someone asked us, like a method is just a function that's tied to a particular object, but you can think of them functionally as being the same thing. Right? There's some function inside phrase called lower, and that's what we want to execute. That's what we want to invoke. And so we run that, and that works, right? So lower is a method of the object phrase, and that works because phrase is of a type, is of this type string, and string has this method defined. So you might look at this and say, okay, right, so lower, is that a Python thing? Like Python gives us this lower thing, and it just is the case that it works for some things and others? No, not really. So if you were to just try calling lower without any context at all, you just type this here and run this, right? So just lower out of the blue, that doesn't work because it's not built into the language. Python has no idea what lower is, right? It's part of it's defined inside this class, or I should say this object. When you execute this line up here, Python goes and inspects this variable and looks for something called lower inside it, but it's not magically part of the language. There's no controlled vocabulary that says like lower is okay to have as a function, as a method, and something else isn't, right? That's defined inside the string class. So this won't work. And also there are other things most types lower will not work for. Like you can't define here's an integer I'm assigning to a variable. Now if I call lower on that, that doesn't work. What's the difference? Well, this is a string. Kind of makes sense for a string to have a function that lowercase is the string, right? It does not really make sense for a number. Like what does that even mean? Like what would you expect a method called lower to do for a number? Nothing, probably, right? So there's no reason to have that. So when you go inspect the definition of integer, you don't find anything called lower. But the really critical part is just that you'll see this dot syntax everywhere in Python, just like other object-oriented languages. And just think of that as like we're looking inside for it's an attribute or a property of this object, as opposed to like len, which is built in. It's just like readily available in the environment. Although sneakily, that is also an object. I said everything is an object, and I mean it. We'll talk about that if we have time. Okay, so you have these objects floating around. Well, how do you inspect them? Like if I want to know what does this object do, how do I do that? There are various ways to do that. I'll show you a couple. First of all, you can always learn the object's type with this built-in type function. So if I have this variable here, I mean, you can see it's a string from the quotes here, but if I didn't know that and I passed this variable to type, it would tell me, okay, this is a string. If I did this, it would tell me that's an integer. If I did this as an empty dictionary, it would tell me it's a dict. Okay, so you can always find out what the type is. There is also a much more powerful tool, a function called dir, which you can, again, apply to any object at all. And this will give you like the full list of everything, all of the attributes contained inside that object. So everything you can possibly do. Now, when you execute this, be aware, you'll see all this stuff that looks like gibberish. Like, why are all these things? Why do they all have these like double underscores, right? These are called magic methods. If we have time, I'll explain them. If not, you can read them. And, ignore them for now, but you'll notice that you have all these other ones that don't have these underscore things, right? And these are all methods that you can call. Now, they may take no arguments or multiple arguments, which is to say they may expect you to pass values to the functions when you call them, but any one of these things in principle can be called as a method. So if I know that there's this encode thing, I can say, a equals string. Actually, let's pick a different example. Let's do is alpha, which you can see there. So if I call that false, okay. Why? I suspect I don't think I've ever actually had a reason to use. Yeah, okay. It's just is alpha. I'm guessing is asking if all the characters are alphabetic, and so spaces aren't, and so it says false if I run this. But if I remove the spaces, then so this. If you had some reason in practice that you needed to know, like, are there any non-alphabetic characters in my string, you would use that method. Right? So there's lots of little helper methods you can use to make your life a little easier. Okay. So keep this in mind. Everything is an object. It may not be clear why that's important now, but if we get far enough into this, then we'll find out. And it's kind of, I think, pretty fascinating. Okay, but let's talk about control flow. Like every language, pretty much, Python has a number of core language constructs that, excuse me, that allow us to control the flow of our code. So the order in which functions get executed, right? So it would be pretty unhelpful to us if the only way you could write code is like linearly, like start to finish, and you have to execute every line in order. Right? Like sometimes you want to call the same thing, but execute the same code multiple times. So you have to have a way of like breaking up the flow of that program. And there are several, actually there's a bunch of the different control flow structures. I'll just talk about the two by far most common ones, one being conditionals or if-then statements, which allow our code to branch. So we can do different things depending on whether a condition is met. So let's say we have this variable mango. We can say if the value of mango is below 0.05, print this, okay? Elif, which is short for else if, so if this condition is not met, but this one is, so if mango is below 0.05, print this. Otherwise, if this condition is met, mango is less than 1, print this thing. Otherwise, in any other case, print this value, right? And so you run that, so you can see, okay, if the value of mango is 0.2, that's what you get. But if I were to make this higher, then a different statement would be executed, right? So again, if you've come from other languages, this will be old hat. Like every language has conditional statements pretty much. Loops are the other big structure, which you again may have seen in other languages. So loops allow us to iterate or loop over the elements of a sequence. So let's say we had a random list from before. Let me just print it again so to remind you. Okay, so all right, there's the list we had. So we might want to do something. It's very common to want to do the same operation to every element in that list. And in Python, that's super easy. You just say for blah in blah, where the first blah is the variable you're assigning to. So you're basically saying, hey, every element you go through in this list, temporarily assign it to the variable named, in this case, element for element, but give me whatever you want. Right, so for every element in the list, random stuff do something. In this case, we're just going to print the value. So this does nothing super interesting. It's basically going through every element and then executing the block inside, and then it's printing that. Okay, you can nest control flow statements. In fact, you pretty much have to at a certain point, unless you're doing very, very simple things, right? So for example, here's a slightly more complex example. What we're doing here is we're going to take that random stuff list, which remember has some integers, some floats, some strings, right? It's a mixture of things. Let's say we only want to pull out the strings in that list. So what we're going to do here is we're going to filter this list. There's other easier ways to do this in Python, but I just want to illustrate the point here. So, okay, what does that involve? First of all, we have to create a new variable to hold the results of the computation. Right? We want something to hold only the strings when we're done. Then we loop over the random stuff list. So for every element in random stuff, do everything inside here. So this will all get executed each time we go through that list. And now we're asking if that element we're grabbing a hold of is instance is a built-in Python function that tells you whether something is of the specified type. So I'm saying, I'm asking, is element a string? Right? So is element an instance of the string class? And if so, only if it is, will this be executed. So if the element is a string, then we're appending to this strings only list, it's the value we have. And if it's not a string, then this will just be ignored, nothing else will happen. And so now, and so notice we've nested a conditional within the for loop, right? So for every element of the list, we're doing something that involves multiple conditions. So a question in MATLAB, you have to note end of for loop with either end or the curly brace. You do not need to do that in Python. This is actually kind of a nice feature of Python. The price you pay for that is indentation is forced on you. And I think I have a little bit on that below. So notice that you can't really avoid indentation. But that's the way that Python makes sure to know that this is where you meant to end the for loop because it's indented. So once it goes back to the same indentation level. So if I write a statement here, that's not part of the for loop, right? If I write it here, it's still part of the for loop. But the nice thing is you do not need to close any really control structure. Notice there's a colon here, and so this colon tells you, okay, now I'm entering the for loop. And then it infers that you've left it when the indentation goes back to where the for loop was. Okay, now there is this nice trick. I mean, there's all kinds of little, obviously, tricks in every language, including Python. But this one is kind of cool. I'll show you list comprehensions. It's just what's called syntactic sugar, which is just, it doesn't change the meaning, but it's just a different way to write the thing you're trying to do. It's a way of expressing for loops in a more compact way. So this single line here is equivalent to the first loop we wrote. So up here, right? So not that it's like much of a difference, right? But here we had like 2 lines. And what this is saying is, so the syntax is a little funky when you first see it. It's in some ways it's sort of inverted, right? But the idea is that you're doing this thing for LM in random stuff. So this is directly equivalent to the first loop we saw. We'll do exactly the same thing. And we can also have nested for loops. We can embed conditionals inside for loops. So here, this example, so this is cool, right? This is now 1 line, does exactly the same as this example. So I'll let you work through this in the interest of time. You can kind of figure that out. But this is nice once you get it down because you can much more compactly write these kinds of expressions. I will say though, this is easily abused. So I personally avoid nested for loops like the plague because they can be very hard to read. And they drive me crazy when I read it. You can have a six deep loop, but you would be crazy to put that in a list comprehension because they get very hard to read. But for like just simple for loops or something like this, where you're just doing like 1 quick check, they're actually quite helpful because you just end up typing a lot less. So you can kind of read through that and hopefully that makes sense. Oh yeah, so this has come up a couple times now. Syntactically significant white space, right? So you might have noticed already, and I mentioned this, that we're kind of indenting our code. You don't get to choose, like you don't have a choice about that. Python forces you to use white space in a syntactically meaningful way, meaning it's part of the language. You can't just be like, okay, I'm going to use I can't do this. Some languages would be able to say like, well, I want multiple for loops to start on the same line. That will not work. You can choose how much you want to indent as long as it's consistent. So I could make this every level increase like 2 spaces or something if I want. Generally speaking, I don't recommend you do that. Like the convention is 4 spaces. I think Russ Poldrack mentioned this morning, if you saw, there is this very widely respected style guide in Python called PEP8, PEP8, which basically says like, unless you have some really good reason to, basically a tab is 4 spaces. So when you indent, use 4 spaces. If you're using most IDEs with a Python plugin loaded like VS Code, Sublime Text, etc., I'm pretty sure, I think by default, that will be set up the way you want it. But be aware, so that's the convention. So you don't get to mess around with white space the way you would in other languages, and that can be frustrating at first, but you will really appreciate it if you stick with Python because it just means when you look at someone else's code, you pretty much know what's going on. Obviously not everything, but you know where like for loops start and end, etc. So it's actually really nice to have that enforced. So I have like a little exercise here. You can modify this to use a different amount of indentation if you want. And then you can also try to break Python by using invalid indentation. Okay, all right, let's talk about something a little different, namespaces and imports. If you're used to languages like R or MATLAB, which many of you probably are, you might expect to have like everything you can do available to you when you first fire up the program, right? So like in MATLAB or R, you can, for example, call like in R LM, right? You can do linear regression out of the box. You don't need to like go around looking for like regression code. It just like is available to you. In Python, the philosophy is very different. Almost nothing is available to you when you start running Python. There's like 70 built-in functions or something. And that's by design. Python, the general philosophy, which I'll come to later, is Python is really software for software developers. It came out of the engineering community, and you can contrast it with like the sort of more science or engineering focused, application focused language like MATLAB or R, right? But differently, like Python is designed to like do it right in some sense, right? And so one of the things people noticed is it's very easy to mess up and can get like pieces of code confused. Like in R, it's very easy to end up with a namespace that's cluttered by like all the packages you've loaded and things conflict and you'll get these messages like this was masked by that and very hard to keep track of what's going on. So in Python, there's this concept of namespacing that's taken very seriously. So if you want functionality available to you generally speaking, you have to be explicit about it. You basically have to say, hey, Python, I want to use this piece of code from this thing over here. And here's what it's called, and I want you to fetch me this functionality. And that's true even of things that are built into the Python language, in the sense they come installed with Python, but they're still not available to you unless you say, hey, I want to use this functionality. And that's by design. It makes it very clear what you're using, and it prevents all kinds of nasty conflicts. But it's another one of those things that may frustrate you when you start out, like, why do I have to do this? And then you go from like frustration to, oh, I get it, totally. I avoid all of these kinds of annoying problems you run into. Okay, how do you do that? Here's an example. The Python standard library, which is all the code that comes with Python when you install it, contains a module called JSON, which if you may or may not be familiar with JSON, it's just a format, it's a plain text format for storing data. It's widely used on the web, for instance. So Python has a JSON module that makes it easy to read JSON files and write to them. And all you have to do, if you want to use that, is say import JSON. Conventionally, you do this at the top of your script. You don't have to, but that's the convention. Is like put all the import statements up top so that people can see that and know what you're using. So in this case, we're going to create a dictionary, and we're then calling from inside this JSON module we just imported. So it's a variable, but the variable is storing a module, which is essentially a collection of pieces of code. We're calling the dump s or dump string function inside that and passing in that dictionary. And so I mean, this will look just like a dictionary, but I can show you this is actually a JSON string. It's a string now. So all that did is it basically converted the dictionary to a string representation in JSON. But if you didn't import JSON, this would not work. This would have given you an error. And you'll see that in a second. Okay. Now you can also import from a module. So here we've imported the entire module, and then we're using stuff inside it, but we can also import things by name from inside a module. So I could say in this case, from collections, so there's another module called collections in the Python standard library, and here we want to import this default dictionary class or object. And so this will work fine. I'm moving quickly just in the interest of time. Okay, and you might think, okay, well, if I import a default dict, then isn't collections automatically available? And the answer is no. Like if I try calling something through collections, I get this error message because I did not import collections. I would have to explicitly say import collections. Okay. Another helpful thing you can do is rename variables at import time. So in this case, I'm importing default dict again, but maybe I think that's too much to type. So I can say import it as dd. And so now I'll only have to type dd instead of default dict. And many packages in Python have conventions about this. So like you'll see import numpy as np all over the place. You don't have to do that, but it's conventional, and I recommend you use the same names everyone else does. That just means that when you see np in someone's Python code, you know they're calling numpy. You don't have to go up to the top and feel like, oh, you're importing that thing. Okay, so that's import. And so most of the functionality in Python is like secretly stowed away inside modules, and you have to explicitly say, I want to use this thing from over here. It's not like R where you just have like 8 million things available to you. But you generally do have all that functionality, you just have to go looking for it. All right, functions. So we've already seen functions here and there. Python would obviously be not super helpful if we already said we could run our code start from top to bottom. So we can define little chunks of code, right? I've already seen like a function like len, for instance, which takes an argument, it takes something and returns a value. But we can also define our own functions. And those are then, they work just like the built-in ones. So here I'm defining a function called useless message. And all it does when you call or invoke it is it prints this message. So it does nothing really helpful. That's why it's called useless message. But it's available to us. It operates just like I called len here. Now I can say useless message. Okay. Now, this is a little bit, we start to get into like conceptually interesting territory. So function arguments and values, return values, right? So functions can accept arguments or parameters that change their behavior. Again, will not be a surprise to many of you. So here, what we're doing is we're defining a new function called add noise, and we have these arguments here. So we have these 3 arguments or parameters we're defining. And so what will happen is that when someone calls this function, they have to pass values in these 3 slots. They have to basically give a value that maps onto x, onto mu, and onto sv. This is just a little Gaussian noise generating function. The idea is that you give me an X value and then I add some noise to that from a distribution defined by this mu and the standard deviation. And the actual hard work is done by this normal variate function defined in the random module in Python. So I'm not writing my own random number generator. Again, lots of stuff is available to you in Python. You just need to know where to look. So all I'm doing is really just writing a very little function that takes a single value and define two other parameters to define the normal distribution and adding noise. So once I run this, notice I have to pass 3 arguments. So what am I saying here? These get mapped 1 to 1. So 7 will fill this X slot, 0 will fill this mu slot, 10 will fill SD. So this is saying take the value 7, sample one number from a random distribution with 0 mean, standard deviation 10, add the two together, and give me back the answer. And there it is. And if I rerun this, because there's a random number generator involved here, I'll get a different number every time. Like the amount of noise is different. But I wrote my own little function to add noise. Now, in this example, all of the arguments are what's called positional arguments, which is to say they have to be passed by position in the function call, and I have to fill all of the slots. Like if there are 3 positional arguments here, this is basically saying there's 3 mandatory arguments. I cannot like choose to not provide. And so if I run this, same function, but I'm calling with only 1 value, right, this gives me the error message, no, that doesn't work. You're missing 2 required positional arguments, mu and standard deviation. So there have to be 3 of them. All right. Now, it would be helpful to be able to say that some arguments are not mandatory. Maybe you don't need, like maybe we want to say like, look, if the user doesn't define the mean and the standard deviation of the distribution, we'll just use like 0 and 1 as the values, right? That's reasonable. We'll assume you want default values. So how do we do that? These are called keyword arguments. So we're rewriting our little function. We've given it a different name because now we're adding defaults, but it's the same function. The only change is we now have these default values here, right? So now instead of just saying like mu, we're saying u equals 0. And that basically means that if no value is provided, then the default will be 0. That's what will be assigned. So now, if we only call this with 1 argument, it still works because in the absence of explicit values, these 2 will be used as defaults. And so it gives you a way of saying, like, the user can specify some variable that controls the behavior of the function, but they don't have to. And if they don't, we have a way of still completing the request. And that's extremely useful because most functions really, in the real world, or many at least, will need to do different things depending on what arguments you provide, but should have same defaults if the user doesn't fill like 50 different variables. Okay, in the interest of time, and also this is conceptually a little more difficult material here, I recommend you read this because you will see this in Python, but you can get reasonably far without it as well. So this will talk about something called argument unpacking, which lets you control with much more sort of flexibility what gets passed in. But conceptually, things start to get a little more complicated here. And the thing I really want to get to, which also is sort of conceptually like a level up, right? So once you deal with classes, you're kind of leveling up in programming. But I do recommend you read that and sort of be aware of what's going on here. But what I really wanted to talk about a little bit, at least, is classes. So now we're going to come back to this thing I said earlier. I said, like, everything is an object in Python. That's really important. And now we're going to explore that a little bit. So, okay, so everything is an object, and somewhere there's a definition of what like a string is and what an integer is, right? Otherwise, they wouldn't behave differently. We wouldn't know what they do. Now we're going to see how these actually get defined. Like, what does it mean to say that something is an object? And how do we stipulate, like, what can you do with an object? So here we're going to introduce the idea of a class. And a class is, you can think of really as just a template for an object, right? It's like almost like a factory, right? So like, when I create a variable, like when I assign a string to a particular variable, that's an instance. It's not the definition of what a string is. It's a particular string. Like the string apple is an instance of the abstract template or class string, which tells you like, what does a string do? What is it? And we can write our own classes. And all of the objects you interact with do have their own class definition somewhere deep in the bowels of the Python interpreter, or at least in the code, the standard library. Okay, so how do we do that? Defining class is actually super easy. Like let's say I want to define a new kind of object called a circle. Right? I just want there to be a circle in Python. This is a valid class definition in just this like 2 lines, and pass is only there for syntactic reasons, because if I just do this, it's a Python's expecting something to come after that colon. So if I say pass, nothing happens. So this is a perfectly valid class definition. And I can actually create new instances of class now, just like I create new strings. I can now create a brand new instance of this class circle. So that's what I'm doing here. The syntax for creating a new instance, given a class definition, is just these parentheses. And you might say, well, okay, but we didn't do that for strings, right? Like we could do something like this. But actually, this is essentially the equivalent of calling the string class and instantiating when this is equivalent. So it's just shorthand because strings are, in some sense, a little special. You can do that, but really what you're doing is initializing a new string with that particular value. So no different here. I'm assigning to the variable circle an instance created on the right-hand side of this new class. And if I ask what is the type of circle, you can see that sure enough, it's circle. But this will not do anything at all. Why? Because we haven't given it any behaviors at all, right? So there's nothing in this, there's just like only what a completely generic object can do in Python is what class or what circle will do, and nothing else. It's kind of a useless thing to write. Like, why would you write a circle for if you're not going to actually give it like circle-like behaviors? So we'll talk about that in a moment. But let me just note before we make do things. Another kind of useful thing to note is the nomenclature, right? So you might have noticed the naming conventions I've used. It's always, for variable names, it's always lowercase everywhere, right? It's lowercase with words separated by underscores. That's called snake case. And again, you don't have to write variable names that way, but it's frowned upon to not, right? And again, it will help you understand when you're looking at a variable versus something else in Python. So do follow that convention. It's not enforced, but it is very helpful, and it will make your life easier and other people's life easier. So one reason I mention that here is because class names are written in something called camel case, which is the first letter is capitalized and multiple rows are just concatenated. So if I had like, maybe a class called big circle, it would look like this. And so one reason for that convention is it makes it so when you look at a line like this, which is a pretty common type of thing to see, it's not confusing to you because okay, this is snake case, this is a variable. I mean, you also know because it's on the left side of the assignment, but you'll know when you see this is a variable because it's lowercase, and this is camel case, so this is a class. Sometimes people don't do this, and actually after a while it starts to really annoy you. Like when I read code out in the wild and often it's like, people who really should know better. And it's just one of those things that starts to get under your skin because you're expecting like a certain thing, and then you have all of a sudden this like, if this were named like that, well, this would break things too. But if it was like that, that would just drive me a little crazy after working in Python for like 20 years. So those are the conventions. All right. But anyway, let's get back to this question, like how do we make the circle do things, right? That's what we're after. So now we'll turn to our definition of the class, and we're adding some stuff here. We'll import math because we're going to need to do something. What I want to do basically is just have a class, circle class that can compute the area of the radius. So if I want to basically be able to initialize a circle, give it as an initialization argument a radius, 3, let's say, and then have a method I can call that computes on the fly the area. And that's what this code does. And the code is very minimal, but conceptually there's some interesting things happening here. So, so there's this init thing, which is, I mentioned, a magic method. So anything that starts with a double underscore and ends with a double underscore has some special behavior in Python. It's sort of part of the Python data model. And if I had more time, I would talk about this at great length, but because it's kind of cool. But just be aware that like this is special, and this init method defines the behavior that happens when you instantiate that class. And so basically, you saw this line here. When this line gets executed, the first stop of call, technically not really the first, but very quickly, what'll happen is that the code defined here inside this init will get executed. And notice this now has a radius argument. You'll also notice it has a self argument. And in fact, inside a class, with some exceptions I won't get into, every method, and remember method is kind of like a function, so I'll just say function. Every function defined inside the class has as the first argument self. And the reason for that has to do with the Python data model, but you can just think of it as it's a reference to it's a reference to the very same instance you're working in, right? So like when this init is called, self applies to the particular circle that's being worked with. And this could, I know some of you probably find this confusing, and this is one of the things that will take you a little while to wrap your head around, but it'll make sense if you stick with it. So just for now, just trust me that like there has to be this like self argument here. And I explained that a little bit more in the text. But the key thing is the second argument called radius is being passed in. And notice now we are assigning that radius value to an internal attribute. Remember dot notation, right? So now we're saying, hey, take the self reference, which is the very same object we're just in the process of creating, and inside that object, store at the attribute r this value. I could have, maybe for clarity, I should have called it radius, but I also kind of want you to get the sense that like, there is no necessary, variable names don't mean anything special, right? You can call them whatever you want. So as long as you're consistent, like you can call this radius, you can call it r if you want, maybe for brevity. So that's the initialization method. All that will happen here is when we create a new circle, that radius will be stored in this attribute r. And now we're also defining another method called area, which has no arguments except self, but self doesn't need to be passed in. Just think of it as like it's just there doing its thing. And so when area is called on a new circle, what's going to happen is this code will be executed. So what we're going to return is pi, which we're importing from the math module. There's the special value, right? The value of pi. And we're multiplying that by the radius squared. Why? Because the area of the circle is pi r squared. And notice that the radius is coming from the thing we've stored internally, right? It's not being passed in by the user. This is not a function. The user is not saying, it's not an area of a circle function that we give it a radius and then it gives us back the value. This is a method called on an object that already exists. We've previously constructed it. And so I know that may be a little confusing. Let's see how this actually works in practice. So make sure we run this code. And now down here. So we're creating a new circle instance. And notice now we have to pass in this radius. If we don't, it'll now complain, just as it did earlier, it needs this value. If there's a mandatory argument radius. And so we initialize a circle with value 4. Okay, let me comment this out. If I just run this at this point, nothing happens. Why? Well, I've created a circle, it's there, it's sitting in memory, but I haven't done anything with it. So now this could be like a year later, I come along and I interrogate that circle. I say, hey, circle, what is the value of r? Remember, r is the name we gave to the radius value stored internally, and it says, oh, it's 4. So this is not doing anything clever. It's just we gave it a value to store. It did. But remember, we also defined this method, which does something a little, at least more clever. It should compute the area. So now we take that object and we say, hey, circle. We call the method area. Remember the dot syntax. We're just saying inside that circle, look for a method called area and then execute it. And now we get actually something potentially useful. Right? So I'm moving quickly, but the point of this is in 5-6 lines of code, we've introduced an entirely new type of object to Python called a circle. We've defined the variables it stores like the radius, and we've created an area method that will compute the area when we want it. And that's what you're seeing here. And we can add whatever else functionality we want, right? So we can do much fancier things. Okay, let me actually do a quick poll. So we have about 20 minutes because I do want to leave like 5 minutes before the next thing. Oh, you know what? No, that won't work. Never mind. I don't have time to log in. So, okay, I'll just, okay. In the interest of time, I'm going to switch to Python for data science because this material fast here is actually quite, I think it's really interesting, but it also it gets a little deeper into the Python object model. If you're interested, I recommend you read it, but you could stop just there and you would already be well on your way, assuming this made sense, which it may not, but work at it. You are well on your way to being able to write classes in Python. If you master the stuff after it, you will actually understand, I think, more about the underlying data model in Python than actually many people who've been writing Python code for quite a while. I think it's kind of fascinating. Let me just kind of give you one teaser, which is that I can't resist showing you this. So, you might see something like this, 4 times 3, and think, okay, that's math, that's arithmetic, it's built into the language, it's special in some way. But no, it's not special. Everything in Python is an object. Even this multiplication operator under the hood is actually this. What's really happening is when you say 4 times 3, the first operand, the first object here, is actually being invoked, right? So basically, it's being passed that operator, which is just aliased to this multiplication, this magic method. That's why it's magic, right? So in essence, when you say 4 times 3, what's actually happening is this 4, this integer object, is we get that 4, we look for the multiplication method inside it, and then we give it what comes after the multiplication as the other argument. And that's true of all the operators in Python. So you might think like, oh, multiplication is like this special thing, it's defined in language. No, somebody had to write an integer class and say that multiplication is a thing you can do to integers. And when you see a multiplication operator, that's just translated under the hood in Python to this multiplication method. So it's really kind of clever, and it has some interesting implications about how you can basically essentially rewrite the Python language so that like operators like division and multiplication, et cetera, do completely different things, which is kind of wild. But I'll stop there. That was just a very brief overview of like some core features of the language, starting with the very, very basic stuff and then all the way through like some fairly sophisticated ideas. And hopefully something in there was useful for you. So let me just switch in the time we have remaining. I will switch to slides. So you can like double click on this Python for data thing, but I'll just switch to slides just so I can sort of go point by point. There's no code in there, so there's nothing to execute, so you don't have to, and then if you don't want. Okay, so hopefully, so hopefully now you're all seeing Python for data science slides. And so what I want to do just in the last really 10, 15 minutes is just like give you some sense of like why you want to use Python for data science or not, right? So I'll try to give you both sides. So and I'll move fairly quickly, but again, I mean, they're just text here, there's no code. So we already saw like why do data science in Python? We saw, relatively speaking, Python is easy to learn. Documentation is really quite good, partly because Python comes out of the software engineering community. People take quite seriously the user experience, and so not all obviously, but the widely used packages are really generally well documented. Because of the size of the community, there's also a huge number of tutorials, guides, other educational materials. So it's easier to learn Python than other languages just because there's so much stuff out there already. It's actually kind of, you have the opposite problem in some ways, right? Like you might already have had the experience like Google Python tutorial, you will literally get like thousands of hits. And then the question becomes like, okay, which of these should I trust? Which are better than others? I've mentioned the standard library a couple of times. It's not available to you, as I mentioned, out of the box when you fire up Python, but if you know where to look, there's lots and lots of super high quality tools, and you should always check the standard library before you start writing your own code, because there's a good chance someone has already written something you need. And Russ Poldrack also mentioned this. So there's the operating systems, OS module, which contains tools for working with the operating system. I mean, these are just some examples. RE, regular expressions. If you don't know what regular expressions are, look it up. They're really cool. They're super helpful. If you do know what they are, now you know where they live. Collections, you've already seen a little bit. There's like extra data structures beyond just like a list and dictionary. Multiprocessing gives you basic tools for parallelization, pickle, JSON, etc. Some of these won't mean anything to you right now. Just main point, be aware that there are like literally, I think there's hundreds actually of modules in the standard library containing all kinds of cool functionality. Beyond the standard library, Python has really, really good, very often best in class, third-party packages for many applications. So you can do lots of things in Python, as I already mentioned. And that's particularly important for data science because data scientists tend to draw on such a broad toolkit. Right? It's not just numerical operations. You might also want like a web server at some point. You might need to do extensive string processing. So there's all kinds of things you can draw on. And there are package managers in Python, Conda and pip being the main ones, that make it fairly easy to manage and install. Most packages will just be like, pip install or conda install, blah, the thing you want, and it will generally work. So some examples of third-party packages, like backend web development, very popular use for Python. Database tools, basically an interface between your data and like SQL. There's tools for scraping, parsing text, working with markup, NLP packages. We'll talk a lot about the numerical computation data analysis library, so I won't really touch on those here. We'll spend like most of tomorrow on that. Machine learning, we'll also talk at great length the rest of the week. Image processing, visualization, etc. So you can just do a lot of things in Python. Python performance is relatively good, which may surprise you because I said it's a high-level language, and that does come at a certain cost. But the thing is, for many of us, much of the time, performance is actually irrelevant in the sense that like what matters is development time, not execution time, right? Like it doesn't matter if it takes 1 hour to run instead of like it would take 5 minutes in C if you save 4 days of debugging and writing code time, right? So like execution time is usually less important. Not always, certainly, but in many cases. Also worth noting that much of the standard library is actually not really written in Python, it's written in C. So it's kind of an illusion. You're writing Python, you're calling Python functions, but behind the scenes, those are just calling C functions that are much more efficient. And so you get a lot of the benefits of C, even though you're not writing C yourself. And that's also true of many of the libraries we'll explore in the course, that they all actually rely heavily on C or C++. It's just kind of like a trick that you think you're writing Python code. I mean, you are, but very often the underlying heavy lifting is done in other languages. Just to kind of give you, this is also to reiterate something Russ Poljack said, if you saw this, and I said just now, which is don't write your own code if you can help it, right? So like you might think, well, yeah, there's a sum function in Python, but it probably does all kinds of extra stuff I don't care about. I just want it very simple, just take the numbers, add them up. So I'm gonna define my own. Well, here's the thing. Here's the time it takes to run the built-in sum. We're summing up like 100,000 integers, like 440 microseconds. That's pretty fast. And that's because it's calling C, although there's probably still some Python overhead. If you write your own sums very naively, it takes you about 10 times as long. This is generally true, right? A lot of the code you call in Python is actually written in C, so don't try to write your own naive implementation in Python. It probably won't run as fast. Of course, there's many times that it doesn't work and you do need to write your own code, but do look first to make sure. Another benefit of Python is actually the community. As Ariel showed you, right, like by some metrics, it's the most popular language. It's definitely in the top 3 by any metric. And the community is huge as a result. And so there's an incredible range of resources. Almost every common problem you will run into has been answered multiple times on Stack Overflow. I'll take this opportunity to mention, a couple of years ago, somebody at some point, like we were doing, like, I think I was doing this tutorial and someone tweeted, like, I didn't realize that like people who know programming still use Stack Overflow, because I think I had an error I didn't know, so I looked up in real time. Everybody uses Stack Overflow and other resources, and you would be crazy not to, right? Now, it's good to understand what's going on, but you definitely want to fall into the trap of thinking like what it is to be a software developer is like to know everything in your head, right? Like, no, I mean, there's a reason these websites exist and you should use them. And every question you could imagine pretty much has been answered already on Stack Overflow. I will say also the community is heavily slanted towards software developers and data scientists as opposed to statisticians or domain scientists. So that is a mixed blessing, right? There's a trade-off. There is poor support unquestionably for stats, for traditional statistics. Things like in generalized linear mixed models, for instance, like imputation, I think R has like 15 packages, there might be 1 in Python. But the quality of software is generally higher in Python, not because of the language, but because the people who write the software tend to come from a software engineering background to some degree. So there's a trade-off like between these 2 types of communities. I'll also mention, if you need more speed, in fact, let me just skip over this because Ariel right now is talking about all the various ways you can speed Python up without switching to a different language. So I would just, like, if this interests you, just watch his lecture afterwards. The main thing I want to kind of touch on here, just in the like few minutes we have remaining, is a comparison between Python and other main languages in data science, which Python competes with. The most notable one being R, and actually maybe I shouldn't say that, like in an imaging context, MATLAB might actually be the most commonly used language, not R. But there are plenty of others, Julia, Mathematica, SAS, Java, Scalix, etc. And so I just want to kind of give you a flavor like what the differences are between a couple of these, MATLAB and R as opposed to Python. Disclaimer, I will try to be objective, but I might fail. That said, I did at one point in my career work in R and MATLAB a lot, or even primarily, so I do think I have some perspective, although I think those ecosystems have almost certainly improved quite a bit since I used those languages. And also, in a few years, I think Julia may be a very serious part of the conversation. There's, I think, good reasons to think that Julia is actually a better language than Python as far as like being a language. It's just that the community is so big and there's so much software out there, there's probably going to be a long, long time before it really makes sense for most people to think about switching. So I'm not going to talk about it here, but be aware there is this sort of like promising new language on the horizon. So R, as many of you will know, is dominant in traditional statistics and also in some fields of science, like genetics. It's very, very popular. Lots of users sort of transition from SAS, SPSS, or Stata to R. And we in the Python community feel like have not been good enough about intercepting. Like, why don't you use Python for some of this? But the main reason for that, I think, and the main reason to use R is because there really is just like unparalleled support. Right? No other language comes close to R in terms of sort of traditional statistical inference packages and all kinds of utilities for statistical inference. I mean, that's really where it shines. And it's also designed to make things as easy as possible for the user, not for the developer. So part of this is, Python gives you sort of solid tools, particularly for a software developer, or you kind of become more advanced and start writing a lot of analysis code. But R really emphasizes like out of the box, easy to do things, even sophisticated things. It's often slow, though this depends. But in general, I think R has some well-recognized sort of bottlenecks in performance. And then the language itself will drive many, many software developers crazy, right? For reasons I won't get into, there's just lots of little quirks about the language that just drive you crazy because it's inconsistent, it doesn't behave the way you would expect, et cetera. But these won't matter once you know the language really well. So I'm not suggesting that's a reason to switch. It's just if you haven't yet developed strong attachment to a language, then R's syntax is sort of, has some, I think many people, including me, don't particularly like it. And also there's just less support for most things non-data related. So it's fantastic for stats, visualization, et cetera, but once you step a little outside of that, support diminishes rapidly. MATLAB, so let me say, I think there's good use cases for R. I think there's really strong legitimate reasons to use R and not Python. I do not think that's true for MATLAB, except for the fact that like if you work in a lab that has like 500,000 lines of code in MATLAB, you should probably use it because that's what you're stuck with. But as far as the language itself goes and functionality, there's really very little you can do in MATLAB that you can't do in Python. There's almost nothing. And MATLAB is proprietary, right? It costs money, it's expensive, the community's smaller. So, again, other than the fact that people in this community already use it and a lot of code has been written, there is really no good reason to use MATLAB as a language. It's just if you're using SPM and that's what you like and know, then fine, but recognize that you're sort of limiting yourself down the line. And we'll talk about alternatives to some of these things later in the week. So I would say MATLAB is not really suitable for use as a general purpose language, and it's clearly playing catch up at this point. I mean, like at this point, MathWorks really sort of looks around, figures out what other languages are doing, and then tries to introduce that. Okay, so why choose Python over other languages? Summarizing. Again, my opinionated view, but there's a reason why we chose Python as the course language. Probably no other language offers the same combination of readability, flexibility, libraries, and performance. So a good way to summarize this is to say it's the second best language for everything. Does not mean you should always use Python. I want to emphasize, right? There may be very good reasons to use other different languages. And a very rough heuristic is like if you're mainly doing traditional statistical inference and you don't need much else, stick with R. Probably your life will be easier. Otherwise, I think Python is the way to go. There are ways you can have your cake and eat it. You can actually interface between languages with something called RPy2, for instance. It's not completely seamless, but in principle, that can be made to work. And the last thing I want to talk about, just very briefly, is just like looking ahead. We're going to spend a lot of time in the next few days talking about various Python libraries. So the core Python data science stack, the scientific computing ecosystem, there's tens of thousands of packages in the kind of the Python as a whole, but several of these really are sort of critical, and you encounter them over and over again. So Jupyter you've already seen. NumPy I will talk about another 2-hour session tomorrow. We'll talk in great detail about NumPy, that sort of basic building blocks of numerical computing. SciPy builds on top of that and gives you sort of additional scientific tools that are more sort of engineering and specific scientific domain focused. Matplotlib is the primary plotter for visualization. We have Kirsty Whitaker will give a nice talk on visualization later in the week. Pandas, I will try to talk about a little bit in NumPy. We don't actually have a standalone Pandas thing, but I am certainly happy to answer questions, and it'll come up in other contexts as well. And scikit-learn, I will do you'll see a lot of scikit-learn. I'll do a 2-hour tutorial on Wednesday, and then like it'll show up in other places too. And then there's various other packages built on top of that. So I will stop there. I won't take questions now just because, well, I can. Yeah, okay, in the interest of leaving time to sort of move between things, I will stop here, but I will stick around and answer, at least in text, any questions that I haven't answered, and do please feel free to ask in the channel for this talk if you have any questions, anything was unclear. And also read those notebooks, because I did try to lay out in much more detail most of what I walked through and a bunch of stuff I did. So I will stop there. Thank you for your attention, and I'll get to these questions right now. And I definitely recommend going. You don't have to go very far. Watching Fernando Perez's talk, I think it'll be illuminating as to like a lot of the philosophy of in the Python ecosystem in Jupyter in particular, which is I think just a really fantastic project on many levels. So I would encourage you to watch that.